Today we're going to talk about functions, the differences between sequences and functions. We're going to find out how to find the rule of a sequence, and we're going to talk about geometric sequences and arithmetic sequences. We don't really need to touch on the quadratic sequences because it's just quadratic. You guys can work those already. Now, the differences between sequences and functions are fairly simple. A sequence is a function, except it's discrete, and the domain of it is limited to whole number positive integers, basically. So 0, 1, 2, 3, 4, 5, 6, 7, on and on and on is all you can have. If you can imagine coming to class, and every day you come to class, I give you a candy bar, that would be an arithmetic sequence. So you come to class one day, you get a candy bar. You come to class the next day, you get another candy bar, bringing your total up to 2. If you come for a half day, you don't get half of a candy bar. I'm not handing you fractions of a piece of candy bar every second that goes by. It's very, very discrete. The day you show up, you get a candy bar. Now, the geometric ones are a little bit more difficult to think about like that, but the experiment that we did with the bouncing ball, you drop the ball, it bounces one time, and it only comes up a certain percentage of the height that it was dropped from. And then after that, it bounces again and only comes up to a certain percentage of the height that it was dropped from. So every time you're multiplying by something, you get a smaller and smaller number, but again, you can't have fractional bounces. You don't have half a bounce, so it comes up this smaller percentage. It's every bounce it comes up that smaller percentage. That basically makes a geometric sequence. So finding the rule for them is different for each one. It's important to remember that from this point on in the book, every time they give you numbers, that's term number 1, not term 0. So it's not your y-intercept or your initial value necessarily when you're writing an arithmetic. So when we go to write these, if we have 2 and 6, we have a 1 and a 2. If we write the arithmetic one first, remember it's not x and y, it's n and t of n. Still our input and output though. 1 is 2, 2 is 6. This is an easy pattern to follow if we're thinking arithmetic because it's just like a linear function. So it's 3, we add 4 to this and get 10, and then 4, we add 4 to it and get 14. Since we are adding 4 every time, that's what's known as our common difference. So that is 4n. Now all we have to do is go back and find where the 0 is. So instead of adding 4, we subtract 4 to get back here. That would be minus 2. We check it out with our table. 3 times 4 is 12, minus 2 is 10. 4 times 4 is 16, minus 2 is 14. That works. So we have t of n is equal to 4n minus 2. That's a rule for an arithmetic sequence. On the geometric sequence, this is going to work very differently. So if I erase these next 2 and I start with the same 2 on here, I have 2 and then I have 6. So what I'm looking for on this one is called our multiplier. So in the geometric sequence, we have a multiplier. To get 2 to 6, we're multiplying by 3. So we'd multiply 6 by 3 to get 18. We'd multiply that by 3 again to get our 4th term. 8 times 3 is 4, 20, that'd be 54. Okay, so we have 1, 2, 2, 6, 3, 18, 4, 54. There's 2 different ways that we can write this. We know we're multiplying by 3. So 3 is going to be our multiplier. I'm going to put that in parentheses. Now, I can either work backwards to find my 0 term. So I divide 2 by 3 and say this is 2/3 times 3 to the n power. That would be t of n is equal to that. Or I can just see which one that I started with, which was number 1, and take n minus 1, and then just put my value here of 2. Either way should be acceptable. They're equivalent. They're going to have exactly the same table, exactly the same values the rest of the way through it. So that should sum up the differences between geometric and arithmetic sequences, and again let you know the differences between this and functions. If we graph both of these, first off, we don't even need the rest of the quadrants. We start at a -2. We go up 1, 2, 3, 4, and over 1, and there's a dot. We graph it as discrete. So all of them still fall in a straight line, it's still linear. but we don't connect the dots. We can have negative y values, just no negative x values. On the geometric, it should all fit onto a curve. So at 1 we're at 2. At 2 we are at 6. And then at 3 we'd be further up here at 18. And if you drew the whole thing, the line through it would kind of come back through here and then go up like that. So it's just like an exponential function. But since this is a sequence, we don't have all these negative values back here. And these just go up. They fit on that curve, but it's discrete. We only have the dots.